15.4 Heterogeneous equilibrium. Many equilibria involve substances that are all in the same phase, usually gas or liquid. Such equilibria are called homogeneous equilibria. In some cases, however, the substances in equilibrium are in different phases, giving rise to heterogeneous equilibria. Whenever a pure solid or pure liquid is involved in a heterogeneous equilibrium, its concentration is not included in the equilibrium constant expression. The concentrations of solids and liquids are essentially constant. Both can be obtained by multiplying the density of a substance by its molar mass, and both of these are constants at constant temperature. Therefore, the concentrations of solids and liquids do not appear in the equilibrium expression. In this example, we have aqueous solutions and we have a solid. You will notice that only the products, the two aqueous solutions, are in the equilibrium expression. The pure solid is not expressed. Here's another example. The decomposition of calcium carbonate is another example of a heterogeneous reaction. We have pure solids and carbon dioxide gas. Omitting the concentrations of the solids from the equilibrium constant expression would give you Kc equal to just the concentration of CO2 gas. This tells us that at a given temperature, an equilibrium among calcium carbonate and calcium oxide and carbon dioxide always leads to the same carbon dioxide partial pressure as long as all three components are present. As long as some calcium carbonate or calcium oxide remain in the system, the amount of carbon dioxide above the solid will remain the same. Sample exercise 15.6, writing equilibrium constant expressions for heterogeneous reactions. Write the equilibrium constant expression for Kc for each of the following reactions. Okay, we're given two chemical equations, both for heterogeneous equilibria, and asked to write the corresponding equilibrium constant expressions. We use the law of mass action, remembering to omit any pure solids, pure liquids, and solvents from the expression. If we look at the first reaction, carbon dioxide is a gas, hydrogen is a gas, carbon monoxide is a gas, and H2O is a pure liquid that needs to be omitted from the equilibrium constant expression. So our expression is then just the concentration of carbon monoxide over the concentration of carbon dioxide times the concentration of hydrogen. For reaction B, we have a pure solid and a gas for our reactants, and our products are also a solid and a gas. So the two solids need to be omitted from the equilibrium constant expression, and we therefore have the concentration of carbon dioxide gas squared over the concentration of carbon monoxide gas squared. Please do the practice exercise. Sample exercise 15.7, analyzing a heterogeneous equilibrium. Each of the following mixtures was placed in a closed container and allowed to stand. Which is capable of attaining the equilibrium? So our reaction is calcium carbonate solid decomposing into calcium oxide solid and carbon dioxide gas. So if we have only pure calcium carbonate in a closed container, is this capable of attaining equilibrium? The answer is yes. Calcium carbonate simply decomposes, forming calcium oxide solid and carbon dioxide gas until the equilibrium pressure of carbon dioxide is attained. There must be enough calcium carbonate, however, to allow the carbon dioxide pressure to reach equilibrium. B, if we have calcium oxide solid and carbon dioxide gas, both of which are the products in this reaction, and a pressure greater than the value of K sub P, or the equilibrium pressure, is this capable of attaining equilibrium? Again, the answer is yes. The CO2 will continue to combine with the calcium oxide until the partial pressure of the carbon dioxide decreases to the equilibrium value. C, if we only have some calcium carbonate and a carbon dioxide pressure greater than the value of Kp, is this capable of attaining equilibrium? This time the answer is no. There's no calcium oxide present, so equilibrium cannot be attained because there's no way the carbon dioxide pressure can decrease to its equilibrium value, which would require some of the carbon dioxide to react with the calcium oxide. So if we don't have both products, calcium oxide and carbon dioxide gas, we cannot relieve that pressure and reverse the reaction to produce calcium carbonate. D, calcium carbonate and calcium oxide. So if we have some of the reactant, calcium carbonate, and we have some of the product, calcium oxide, can this attain equilibrium? The answer here is yes. The situation is essentially the same as in A. The calcium carbonate is the only reactant, and it will freely decompose until equilibrium is attained. The pressure or the presence of calcium oxide initially doesn't make a difference here. The only thing that matters is that we had the reactant present and it is capable of decomposing. Please try the practice exercise.